In this video, we're going to discuss some basic concepts related to hypothesis testing and confidence intervals for a mean. A hypothesis is a tentative explanation for a specified phenomenon or group of phenomena. When conducting hypothesis testing for a mean, we need to consider our null and alternate hypotheses. HO, our null hypothesis, or statement of no effect, contains the statement of equality. Ha, our alternate hypothesis, is where we usually find the claim. However, the claim is sometimes found in our null hypothesis. As you work problems, you want to pay careful attention to the context of each one. But most of the time, you will find the claim in our alternate hypothesis. Our p-value is the probability value compared to the sampling distribution and based on the population parameter given in HO, our null hypothesis. Statistically significant. Any p-value which falls below the predetermined threshold of significance, Greek letter alpha. Common alpha levels are 10%, which corresponds to a 90% confidence interval, 5%, which corresponds to a 95% confidence interval, and 1%, which corresponds to a 99% confidence interval. When conducting hypothesis testing and confidence intervals for means, we take into consideration the central limit theorem for a mean. The central limit theorem essentially states that when a random sample is taken from a population with mean, mu, and standard deviation, sigma, its sample mean, given by x bar, has a sampling distribution with the same mean, mu, but a standard deviation, also known as standard error, of sigma divided by the square root of n, which is our sample size. The shape of a sampling distribution will be approximately normal if our sample size is large enough. For means, we estimate the population parameter sigma with S, our sample standard deviation based on the data, standard error of x bar equals sigma divided by the square root of our sample size, n. The sample standard deviation is the same thing that we referred to in the first paragraph, our standard error, again given by the formula sigma divided by square root of sample size, n. This is a very important formula. When conducting hypothesis testing for means, it's necessary to use the student's t-model. Student's t-models comprise a family of distributions and rely on the degrees of freedom parameter. The degrees of freedom are found by taking n minus 1, that is, our sample size minus 1. Here's another way to think about the central limit theorem. With repeated sampling of a population, the mean of all of our sample means would resemble a normal distribution. The standard error is the standard deviation of this collection of sample means. When conducting hypothesis testing for a mean, we must also consider certain assumptions and conditions. The first is independence. Can it be reasonably assumed that the data values are independent? Next, randomization. Has the data been sampled randomly? 10% condition. The sample is no more than 10% of the population. Nearly normal condition. The data come from a unimodal, symmetric distribution. Let's try a couple of sample problems. First, let's find a confidence interval. Given that sample size n equals 100 and sigma, our population standard deviation, equals 1200, find a 98% confidence interval for the mean price, $23,353, of a 1 to 3 year old used car. The first step is to find the critical value of t. There are a couple of ways that you can do this. You can use a t-table, which would be found in the statistics textbook if you happen to be taking a class at the moment, or you can use a graphing calculator. The graphing calculator command is as follows. On a TI-83 or TI-84 graphing calculator, you would type in second, distribution, and then select option 4 for inverse t. Once you access inverse t, you'll type in .01. This represents, we have 98% in the middle, then we have 1% on each side. So this represents the percentage found in one of the tails on the confidence interval. We do this to establish the lower boundary or cutoff point on our confidence interval. Next, if you have one of the older model calculators, you'll type in a comma, or for the newer calculators, just arrow down to the next field. Then you'll put in your degrees of freedom. If our sample size is 100, and degrees of freedom are found by taking our sample size minus 1, then we know our degrees of freedom are 99. From here, simply press enter. The critical value of t is approximately 2.36. If you put in 0.01, you'll get negative 2.36 because it's giving you the critical value of t on the lower end of your distribution. From here, you can just use the positive or absolute value. If you'd rather see a positive result, when you do inverse t, you could also type in 0.99 for the 99th percentile, and then your degrees of freedom 99. That would give you positive 2.36. Most people just type in 0.01, get a negative value, and then just rewrite it as a positive for the purpose of calculation. If you don't have a graphing calculator and you don't have a statistics textbook, you can also find t-tables online very easily through a simple web search. Now we have all of the information we need to calculate our confidence interval. We'll use the following formula. X bar, our sample mean, plus or minus our critical value of t, multiplied by our standard error. When we plug in our values, we get, for X bar, 23,353, plus or minus that critical value of t, 2.36, multiplied by our standard error, which is found by s divided by square root of n. That's 1,200 divided by the square root of 100. When I calculate my value for the lower bound of my confidence interval, I use the minus sign. So in other words, in my calculator, I type in 23,353 minus the product of 2.36 times 1,200 divided by the square root of 100. This gives me a result of $23,069.80. When I calculate my values again, using the plus sign, I have 23,353 plus 2.36 times 1200 divided by the square root of 100. This gives me the upper bound of my confidence interval, which is $23,636.20. So we've calculated our confidence interval. The lower bound is $23,069.80. The upper bound is $23,636.20. What does this mean? We can conclude that with a confidence interval of 23,069.80, 23,636.20, that we are 98% confident the mean price of a 1 to 3-year-old used car is between these two values. We can also solve this problem easily using a graphing calculator. To do that, you'll enter the following commands. You'll go to Stat, Tests, and then select option 8 for T interval. Next, you'll enter in the fields X bar, 23,353, that's your sample mean. Then you'll be asked to enter your standard deviation, which is 1200. You'll be asked to enter the sample size, which was 100. And then you'll be asked to select a C level. That's your confidence level, which in our case was 98%. We'll enter that as a decimal, 0.98. Finally, you'll hit Calculate. And that will give you the same result. Now let's take a look at an example where we conduct a hypothesis test. A recent report from a consumer information website stated that the average family of 4 spends $770 on groceries each month. An instructor for an extreme couponing class claims that a recent group of 12 students now spends significantly less money per month on groceries after taking her course. Given that our sample mean is 608.75, our sample standard deviation is 44.83, and our alpha or significance level is 0.01 or 1%, test the instructor's claim. First, we need to set up our null and alternate hypotheses. Our null hypothesis is that mu is equal to 770. This is our population mean.
Am I still signed in?
Our alternate hypothesis is that mu is less than 770. The reason we choose a less than, or left-tailed test, is because of this statement. A recent group of 12 students now spends significantly less money per month on groceries. Less than generally indicates a left-tailed test. Next, we need to find our t-score. The t-score is given by our sample mean minus our population mean divided by our sample standard deviation over the square root of our sample size, n. Plugging in our values, 608.75 minus 770 divided by 44.83 divided by the square root of 12. Calculating this, you should get a result of negative 12.46. Using our t-score of negative 12.46, we can find the probability. When we find the probability in the context of this problem, what we're essentially trying to find out is, given that when we calculate our probability, what we're trying to determine is whether or not students of this extreme couponing class really are spending significantly less when compared to the population mean of $770. If the probability value that we generate is less than 0.01 or 1%, then we'll know that the instructor's claim, that we can support the instructor's claim based on the data. If the probability value is greater than 1%, then the instructor's claim is unsupported. So let's calculate the probability. You can use a table, or you can use your calculator. Using the calculator, you'll type in the following commands. Second, distribution, and this is with a graphing calculator, TI 83 or 84. Second, distribution, normal CDF. We'll establish a lower and upper bound. Your lower bound, we'll use negative 100. And actually, any value, negative 5 or below, will work. We just need to establish a value that's off the lower end of the curve. Our upper bound, we'll put negative 12.46. And we'll calculate.
Are you good with little or?
When we calculate this, we get a probability value of 0. Comparing our probability of 0 to our alpha level of 0.01 or 1%, we can conclude that the sample evidence does support the instructor's claim that students save significantly more money on groceries after taking her course. In other words, we can reject the null hypothesis. Our conclusion. Again, the probability value of 0 is less than alpha of 1%. Therefore, we reject the null hypothesis. The sample evidence supports the instructor's claim that students save significantly more money on groceries after taking her course. We can also solve this problem very quickly using a graphing calculator under the Stat Tests menu, as long as we have our summary statistics. Here's how we do it. You would type in the following commands. Stat, tests, option 2, which is a t-test. This is for a TI 83 or TI 84 graphing calculator. Our null hypothesis, symbolized in the calculator by mu null, mu sub 0, we'll type in 770. Our sample mean x bar, 608.75. S sub x is our standard deviation of x. That's 44.83. We type in then the sample size, n equals 12. Next, you're asked to select less than, not equal to, or greater than. So you'll use your arrow keys to highlight the less than, and select less than mu null. Finally, you'll hit calculate. Once you calculate, your p-value, if you're using the calculator, will be decimal 7039, which is essentially 0. You would then state your conclusion as we have outlined here. All right, so those are some of the basics for hypothesis testing, finding confidence intervals for a mean. We looked at some basic terminology, an example of a confidence interval, and an example of conducting a hypothesis test.